Exponential form versus logarithmic form. The blueprint is the first I call it a two-way street. B to the x equals n. Think of it as base to an exponent equals numerical value. Those three components, if rearranged, can be written in a logarithmic form. Log base b has a numerical value of n. And basically what a logarithm is, it's an exponent. It's the power that b needs to become n. Let's practice a few translations. For example, we know 3 squared is equal to 9. And if you take that equation, but you write it in logarithmic form, 3 is your base, 2 is your exponent, n is equal to 9. That's your numerical value. So basically what you would do is you'd write log, take your base number, your overall numerical value, and that's equal to the exponent that it takes 3 to become 9. And since 3 squared is equal to 9, your logarithm is equal to 2. Now, if you go the other way with it, maybe you have a logarithm and you wanted to write it as an exponential, and that's very helpful, by the way. On the right, we have log base 9 of 1 equals 0. When you translate this back to exponential forms, just be careful to line up your bxn correctly. 9 to the 0 power is equal to 1. And so those are really the blueprints to convert one form to the other. The bottom half of the page, we're going to do a few evaluations. Evaluate log base 2 of 16. Now we don't know what that's equal to, so I'm just going to put equals x. Translating this, translating this to exponential form will make it easier to solve. Our base number is 2, our overall numerical value is 16, and again with logarithms, it is a missing exponent that you're after. Since 16 is 2 to the 4th, and we remember that 1-to-1 property from the last video, if the common base is 2, then we can set the exponents equal. And so this problem has an answer of 4. And sure enough, that's the correct answer. 2 to the 4th power is equal to 16. The other logarithm problem, again, we don't know what the answer is, so I'm going to put an x because a logarithm is a missing exponent. Translate this. 4 to the x equals 2. 4 to the x equals 2. Well, 4 is 2 squared. 2 is 2 to the 1st. And so that tells us that 2x has to be equal to 1. Set the powers equal from the 1-to-1 property. 2x equals 1. And that tells us that x has to be a half. A power of 1/2 is the same as a square root. So 4 square rooted is equal to 2. In the previous video, we looked at graphing exponential functions. The inverse to those are logarithms. And so let's also remember that when you have inverse graphs, that they are symmetrically split by the diagonal line y equals x. So let's compare and contrast y equals 2 to the x and compare that to log base 2 of x. Okay, so in blue, let's do the exponential. Remember horizontal asymptote along the x-axis. crosses at 0, 1, and then just takes off. From what we know about inverse graphs, we do know that there is a diagonal that acts as a mirror where a graph and its inverse are reflective of one another. Let me try to make a better X real quick. There we go. Now in red, we'll do the logarithmic graph. Instead of having a horizontal asymptote at y equals 0, there will be a vertical asymptote at x equals 0. Instead of a y-intercept at 1, there will be an x-intercept at 1. All those roles change hands. Okay, so let's remember the exponential. I'm going to keep it color-coded. We had the domain for the exponentials with all real numbers. That blue graph covers every x-coordinate, negative, 0, and positive. The y values are only covered for positives. And there was a horizontal asymptote at y equals 0. Now, for the logarithm, the domain, only the positive x's are covered. Note that the graph covers all y values, the negative y's, 0, and positives. Inverse functions will swap domain and range. Let's also note that there's a vertical asymptote at x equals 0. Asymptotes also reverse. Inverse are very predictable. And I'm going to try to bold up that graph a little bit. There we go. All right. There is a feature on your graphing calculator that will help you. Before I do that, let me also make a note of y-intercept and x-intercept. There we go. Okay. Not all graphing calculators have it, but if you have it like a TI-84, a TI-84 Plus, these will have a feature called log base. Now to get to that, let me change colors here. To get to that, mercy, I'm having trouble writing on this slick screen here. Sorry about that. Hit your math button. It's quicker to arrow up, but it's option A. And you will find log base if your calculator has it. If you have an 83, it's probably not going to be on there, but I believe all the 84s have it. When you hit enter, you will get log. There will be a box for your base and a box for your n value. This is very helpful when you get ready to graph logarithmic functions. Suppose you wanted to graph the logarithm above, which was log base 2 of x. You would go to y equals, clear out any old functions that you have. Using the math arrow up log base, you will have y equals, and then whatever your problem gives you, like this one gave us a base of 2, you would put in 2 in the subscript box, and then in the parentheses you would just put the variable x, graph, and you will see the graph of that function. If you don't have log base, there's a way around it. Your log button next to your 7 divided by the log button again, that's called change of base formula. So for this problem, you would just simply put a 2 there. Your x and your 2. That's the way to get around if you don't have log base as a calculator function. Sketch the function log base 3 of x minus 2. If you go into your y equals screen on your graphing calculator and use the log base function from hitting math, arrow up, and option A, you can enter the 3 in the subscript and the x minus 2 in the set of parentheses, hit graph, and things will be going okay. If you do not have log base on your calculator, that is fine. The way around it is log of x minus 2 over log of 3. You can type that graph, or that, excuse me, you can type that function in either way. Now once you graph this function, you will see that the vertical asymptote gets moved around. In fact, it is now located 2 units over, and instead of the y-axis being the barrier or the asymptote for this graph, the line x equals 2 has now taken its place. Your graph will still have the same characteristic look. It's just the asymptote and the intercept have now moved. The domain, this graph only covers x values from 2, actually larger than 2. It doesn't even count 2. That's why I'm using parentheses. So anything greater than 2, your graph will cover in the x direction. The range, all real numbers, because the graph covers negatives, positives, and even 0 in the y direction. The vertical asymptote is x equals 2, and the intercept is just 1 unit farther over, so 3, 0. Now let's investigate the way to find the vertical asymptote and the domain without necessarily graphing. we had log base 3 of x minus 2. Okay, now this part of your logarithm has to stay positive. Like if you were to simply on your calculator type in log of 0 or log of a negative number, you wouldn't get a real number answer. Logarithms are only defined for positives, so you got to keep that in mind. Specifically for this function, x has to be greater than 2. Now that's where you get your domain, but you can also use that number 2 to mark off your vertical asymptote on the graph. Exponential functions are one-to-one functions. The graphs of them pass both vertical and horizontal line test. Same thing's true with logarithms. Now let me casually mention, when you see ln, that is a logarithm with a special base number e, Euler's number. Don't let the ln throw you off. That's just one special type of logarithm. Another thing to keep aware of is if you see log without a base number, it's an assumed 10. That's a common logarithm. Natural logarithm has a base of e. Common logarithm has a base of 10. Any other base, you will see a number like 2 or 3 or 5 or whatever. Because logarithms are also one-to-one, you can set those parts equal to one another and solve. If you get a logarithm that's the same base, in this case they're both natural log, you can set those equal to one another and solve. The thing to be careful of is make sure that the answer you get is in the domain of the logarithm from your original problem. Natural log of x minus 3 has a domain of 3 to infinity, parentheses 3 to infinity. Well, since 7 is larger than 3, 7 minus 3 creates a positive 4. All's good. Logarithms like positives. On this one, x squared minus x can be set equal to 12. That's a quadratic equation, so we bring 12 over, set equal to 0, and we can factor with a minus 4 and a plus 3. Set each one equal to 0, and we will get answers of 4 and negative 3. We may get to keep both of these. We may not get to keep either one. We have to test them. In here, 4 squared minus 4 is positive 12. So this one's a keeper. This one's a keeper. We plug it in. We maintain positive values. 4 squared minus 4 checks out. Negative 3 squared is 9. Minus negative 3 is also positive 12. So it turns out we get to keep this one as well. With logarithms, you have to check your answers at the end to make sure that you maintain a positive value in the original problem, as well as a match, but they have to remain positive. If we'd have gotten an answer of x equals 0 at the end, 0 squared minus 0 is 0. Well, logarithms don't like 0, so we'd have to have thrown that one away. But as long as the answers you get at the end stay positive once subbed back in for your variables, you get to keep them.